Okay, welcome back, guys, to another exclusive episode of this tutorial. So, if you have been following our videos, we have treated the first law, the steady flow energy, the non-flow processes, and also the air standard cycle. So today we'll be treating the vapor power cycle, just like the air standard cycle too. So the first on the list is the Carnot cycle. Okay, so we are going to look at the processes involved in Carnot cycle and how to tackle questions based on the processes. So what is a Carnot cycle? A Carnot cycle is an ideal cycle in which heat is taken at a constant upper temperature and rejected at a lower temperature. So what do I mean by this? Mathematically, I can say that for a gas, let's start with assumption for a gas. Okay, so for a gas we have that, draw this, you draw this too. So here you draw this, come here, you draw this too. Okay, now you come and join them, and you join here too, okay. Alright, so let's take, assuming it's here for a gas. Okay, so just like we defined it, it works at what? It works at a constant what? Temperature. So if this is 1, 2, 3, 4, you see that this is a TS diagram. You see that T1 is equal to T2 and also T3 is equal to T4. Alright, and entropy, S1 equal to S4 and also S2 equal to S3. Alright, now having said this, you know that from the previous video and from all that we have done so far, you shouldn't forget the formula of the efficiency of a machine or a system remains heat network over heat supplied, where heat supplied is QS and network is QS minus QL over QS. QL is heat lost, of course, sorry, heat rejected. So now recall from the non-flow process, one of the process, which is the isothermal, the heat is given by T, change in entropy. Remember this formula from isothermal process. So since it's a gas, we can say that the efficiency is heat supplied is what? T1 S2 minus S1 minus heat rejected is at the lower temperature, Ts3 minus S4, okay, all over T1 S2 minus S1. So but since S2 equal to S1 is equal to, or rather, let's say, since S2 minus S1 equal to S3 minus S4, we can say that this becomes T1 minus T3 over T1 when S cancels out. When you factorize them out, S1, S2 minus S1, factorizing out, they will cancel out. So finally this becomes 1 minus T3 over T1, okay, but you know that T1 is equal to T2, so we can also say that efficiency is 1 minus T3 over T2. So this remains the formula we can use to find efficiency even at the vapor state. You can use this to find the efficiency of a Carnot cycle because we assumed for a gas, we are going to still do for a vapor, okay. So this assumption is based on a perfect gas. So now let's assume the Carnot cycle is working in a vapor state, okay. Let's do that assumption. We'll have that. So for a vapor state, for rather Carnot cycle for vapor, let me do something like this. Carnot cycle for vapor is given by this. So we are going to draw our TS diagram. Our TS diagram, of course, always in the balance. Okay, so we have something like this. Okay, now this side is called the wet region. Okay, now here is called the saturated liquid region, and here is called the saturated vapor. Then this space here is the superheat or superheated region. Okay, all right. Or rather, I can say something like this so that it will not complicate things. So instead of saying the region, I can decide to say this is the saturated liquid line. Okay, saturated liquid line. So anything that falls, like here now. This is the 1, this is the what 2, this is the 3, and this is the 4. Okay, this tip falls on the line, the liquid line, and this other tip falls on the vapor what line. So then this space is the what superheated region. So this remains T1 equal to T2, and this also remains, so this is a TS diagram. This remains T3 equal to T4. Alright, now what's the meaning of all this? Someone might ask, what are we doing? Why the diagram? What does this diagram mean? So from the diagram, process 1, 2 is isothermal plus constant temperature, isothermal heat addition. Okay, process 2, 3, process 2, 3 is the isentropic expansion. The process 3, 4 isothermal heat rejection. Then lastly, process 4, 1 is the isentropic compression. Okay, now the heat supplied, or rather here as a thermal heat addition, Qs is given by H2 minus H1. Come here, work expansion, that is isentropic expansion, W2 3 is equal to H3 minus H2. Here Q 3, 4 is equal to H4 minus H3. Then W4, 1 is what H1 minus H4. Okay, this is what we are going to be using to solve examples now. So without taking much of our time, let's take an example to illustrate this. So we have this Carnot circle, assuming it as a gas and also assuming it as a vapor. So let's take an example to illustrate this more. So let's go over and take an example.
It leads to liquor and some ladies. Yeah, we they turn up on a daily. It's how I walk up. Yeah, soft walk.